Okay, so in this video I'm going to just run through a bunch of examples of finding volume. So you should be getting, at this point, if you're watching this video, you've watched some other ones and you're getting better at finding the volume. And you should have an idea of the three different methods. There's the washer-disk method, which is really one method. You use the washer when there's a hole in the middle. You use the disk when there's not a hole in the middle of your 3D shape. Then there's the shell method, and that is used for whether you have a hole or not, you use the same method. And these two together are two different methods that are used when you're rotating things. So anything you can do with the washer-disk method, in theory, you could do with the shell method also. And the reason why we have two different methods for handling the same type of problem is because sometimes one of these methods will produce an integral that's going to be difficult to integrate, or sometimes it's hard to get a pulse on how to write the formula, or sometimes with one method we're going to have to use two different intervals or maybe three different intervals, and so we use the other one because it might only need one interval. But both of these are used when we're rotating around something. So if we have a region that we're rotating around a line of rotation, either one of these in theory could be used. And then the third method is the cross-sectional areas. So that's, you don't use that when you're rotating things. It's just a different way to create a 3D solid. And in that case, we're taking a flat surface or flat region and we're pulling shapes up out of it. And we call those cross sections, of course. And that's, so we'd use this for that. And this has a bunch of different formulas depending on what the shape is that you're pulling up out of the flat surface. Okay. So that was just a quick run through of all the three methods that we've talked about. So now we'll read this one. Consider the region bounded by the curve y equals e to the x, and I generally like to draw a picture as I go. So y equals e to the x looks something like that. The x-axis, so that'd be along here, and the lines x equals -1. Oh. So I'm going to continue this on down, and x equals 1. That's fun. So that region, the region we're talking about, if I grab a highlighter, is all this stuff in here. Okay, that's the region that we're talking about. Nope. Okay. What are we going to do with that region? It says find the volume of the following solids, including sketches. Okay, there's my little beginning of the sketch. The solid obtained by rotating the region about the x-axis. So the fact that I'm rotating it means I'm going to use either washer disk or the shell. Now the first thing I ask myself is there going to be a hole? So in this case, notice the x-axis is my line of rotation. So the region is touching the line of rotation the entire way, which means there is not going to be a hole in the 3D solid. So this is going to be a solid 3D solid. There's no hole. And you could try to picture this. Again, if you understand these methods, drawing the 3D shape may or may not help you. Because once I realize that it's a rotating thing with no hole, then I immediately think I either use disk or shell method. If I'm going to use the disk method, then I know that that's pi times the integral of radius squared times some little change in the radius. Because remember, what we're adding up, because that's what you always want to ask yourself, is you're adding up these little small disks, which are basically mini cylinders, and the volume of the cylinder is pi r squared times height. So the pi is right there. The r squared is the thing squared, and the h is this little thing here, right? And so we're looking at this, and notice I drew that disk the wrong way. The disk is actually going like this, isn't it? Oops, like that. And so the little bit of thickness is in the x direction. Okay? So that means that this is going to be dx. Which immediately, if you remember from the other video, if this is in terms of x, that means if we were to use the shell method, that would be in terms of y. And I might just do both here just to again, give you one more comparison. But it looks like the distance method is going to be pretty easy, so that's probably the one I'd use here. Okay, so now all you have to do is figure out the radius. Well, the radius is just the distance, for the distance method, the radius is just the distance from the line of rotation to the outside edge. And you can see some examples of the radius here, right? Looks like the radius is always the distance between this line and that line. Well, that's just y equals e to the x and y equals 0. So e to the x minus 0 would be e to the x. So my integral is, and then we got to do the limits of rotation. I mean the limits of integration. So since this is in terms of x, we just got to look at the region and say what x values cover that region. Well, we start here at -1 and we go to +1, right? So that means my limits of integration are going to be -1 to +1. And that would be my integral for if I'm using the disk method. Now, if I'm using the shell method, quick little reminder, that means that I'm going to be creating these shells. Again, I'm rotating this way. So I'm going to be creating these shells that look kind of like this, right? I drew it the right way this time. And notice the little change is in the y direction. So if I'm using the shell method, my integral is going to be 2 pi times radius times height plus a little bit of thickness. In this case, it's dy. Okay. Now remember where that comes from is the volume is equal to, if we were to slice this and lay it, slice it down here and lay it open, we'd have a big rectangle with a little bit of thickness, and the width of the rectangle is my height, and the length of my rectangle would be the radius, would be the circumference, which would be 2 pi r, and then we got that little bit of thickness, and that's where the d something comes in, right? So you can see there's the 2 pi right there, the r is right there, and the h is right there. So we just got to fill in the r and the h because we already got the little bit of thickness with the dy. Okay? So again, if we erase some of this stuff, just so we can clear it up. There's the y-axis again. So this is a little bit harder to picture for a lot of people. So if we're rotating around the line of the x-axis, if we pick some random space in the middle here, this is what my shell is going to look like. Okay? So notice the height is right here, and the radius is right there. That was really poorly drawn. Let me do a better job of this. I made it too big. There we go. Okay? So the radius is just the distance. Notice the radius is just y, right? Because I'm going from x, or from the x-axis to a certain point where the shell is. Because remember, picture those nesting dolls. So this is one shell. There will be another one outside of it, another one outside of it, and it'll fill in this whole space. So the radius is just always going to be y. And now here's where we see why we would not want to use the shell method here. Because notice that for a while, the height is just 2, because it's going from -1 to 1. But at a certain point, right about there, to blow this up quite a bit, at that point right there, the radius, or the height, stops being 2, and it becomes something else. It changes. See how it's getting smaller? The height's getting smaller as we go out. So in this case, I would have to use 2 integrals. So I'd have to put a little plus here, 2 pi integral, and the radius would still be y, but the height is going to be different for this one than the other one. So in this case, my limits of integration would go from 0 to whatever that is. 0 to that point right there would be e to the -1, right? Because that's what the y value is. And so that means this guy's going to go, and the height for all that would always be 2. So that first one's going to be a fairly easy integral. But this one is going to go from e to the negative 1 up to here. So we're integrating. Let me get a different picture. Draw. So the second integral is going to go from there to there. So that's going to be e, well, just e, because that's e to the, we're plugging in 1 for each function, right? And my height is going to be, you want to find that distance right there, it's going to be 1 minus e to the y. Or no. It's going to be 1 minus the x coordinate of that. So now, again, this is showing you why we do not want to use the shell method in this one. So the x coordinate of that guy, remember that coordinate is going to be, in terms of y, is going to be natural log of y comma y, right? Because if it's y equals e to the x, that means it would be natural log of y is equal to x, right? Because the natural log does e to that. So that means this is going to be 1 minus natural log of y dy. So again, that was tough to set up, and this is going to be a hard integral to solve. So in this case, we definitely want to use the disk method. See how much easier the disk method is than the shell method. Now some of you are probably saying, well, I don't like the shell method anyway, so I'm never going to use it. Well, this is just an example where the shell is harder, but there are plenty of other examples where the disk method produces something that's also difficult. So, okay. All right. So I'm not going to do the disk and shell every time, because you don't want to do that every time. You want to pick out the one that's easier. So if you, basically what you do, if you start down one and it seems like it's getting complicated, then you switch to the other. Okay, the solid obtained by rotating the region about the horizontal line y equals negative 5. So this is the same drawing, where that's negative 1, that's 1, and this is the line y equals e to the x, right? But now we have a horizontal line down here at negative 5. So that's definitely going to have a hole in the middle. So that means we either have to use the washer or the shell. We'll start with the washer, because that's in terms of x, we know, because of we're still rotating around a horizontal line. So that means we need pi times the integral from big R squared minus little r squared dx. And again, how do we know it's dx? Because we're rotating around a horizontal line, which means my washers are going to be stacking like this instead of like this, which means that little bit of thickness is going to be in the x direction, not in the y direction. Okay. So I need a big R and a little r. The little r is the easiest one to do here because you can see it's the same all the time because the inside edge is parallel to the line of rotation. And that's just going to be negative 5. 5. We're talking about distance here. It's just it's the distance from 0 to negative 5, which would be 5. So we put 5 in there. And the big R is going to be, let me erase my 2. The big R, if we grab a different color real quick. The big R, one example would be this guy. Another example would be this guy. Oops. So notice the big R is being determined by that line. And so we know that this has got to be 5, of course, because that's this part here, plus this little part here, and that little part is just the y coordinate of any point on this line. And again, the points on this line are x comma e to the x. So the y coordinate is e to the x, so we just need a little e to the x there. And that would give me the equation for finding the volume. Now notice the shell method I'm not even going to attempt, because if this is in terms of x, that means the shell method is going to be in terms of y, which means we're going to involve a natural log of y, and we don't like to integrate natural logs that much. So at least I don't. Okay, so that's the washer method. Let's move right along. Draw, and again, I'm not doing any of these integrals. They should be pretty basic, and you can do them. So I'm just trying to help you get the setup, because that's really the new learning part here, is getting the setup. At this point, you should all be experts at taking integrals, and most of the integrals in these problems are not that challenging. There'll be a few, but most of them are not. Okay. Draw a sketch of the region in the xy plane bound by the curves y equals x squared and y equals 5 minus x squared. Find the volume of the solid whose base is the region. Okay, here's the cross-sectional area, and whose cross-sections perpendicular to the x-axis are squares with one side in the xy plane. Aha. So first of all, we're going to draw. That's my favorite color. Dark blue, that works pretty good. Okay, so first of all, y equals x squared, we know looks like this. And y equals 5 minus x squared would look something like this. Because I'm starting at 5 and the x squared is upside down, right? Again, you notice I'm being real rough here. I don't have to be exact. I just need to know what the basic shape looks like. And then I need to find the intersection points. These actually probably intersect at the level, so that's really a horrific drawing. Okay, so we need to find these endpoints so we can define our region. So we know that those endpoints occur when x squared is equal to 5 minus x squared. Okay, so if we add x squared to both sides, we get 2x squared is equal to 5, which means x squared is equal to 2.5, which means x is equal to plus or minus the square root of 2.5. Okay? So that means that this point occurs at the square root of 2.5, and this point occurs at negative square roots of 2.5. Okay? So we just did that little bit of algebra to find where those endpoints are, and that's going to be helpful for determining the region and our limits of integration. Okay, so now, find the volume of the solid whose base is the region and whose cross-sections perpendicular to the x-axis, so they're running this way. So I breathe a sigh of relief, because that means that all the cross-sections are going to be determined by the same set of lines. Let me use some different colors here so we don't get confused. So there's a cross-section, there's a cross-section, the base of the cross-section, I mean. Okay? And they're squares, so that means we have like a square coming out of this thing. Here's another example. So you can kind of picture them. They have a little bit of thickness. Where is the little bit of thickness? A little bit of thickness is in the x direction. So this is going to be a dx. Okay? Which is nice. We don't have to change these around. So these are already in the right form. So we know that, and we know that this is a square. So that means it's just going to be side squared, right? We don't need any pies or anything like that, because it's just we're finding the area of the square and multiplying by a little bit of thickness, and that's the dx, is the little bit of thickness, okay? So now all I have to do is figure out the side length of each of these squares. And notice that, that's what I was saying earlier, we're happy that it was perpendicular, because if we're looking at one of the squares, grab highlighter, that line right there corresponds to these lines, right? So notice as we run through the region, my base is growing for a while and then shrinking, and that's making my square small at first and gets bigger and bigger and bigger and then comes back down. Okay? And again, if you need some help visualizing these, there's a video that's completely committed to those visualizations, so you can go look at that. Okay? So now we're going to go ahead and write the integral. Notice we need to find an expression for the length of that orange line, the blue line with the orange highlighted, right? And here's the cool thing is it looks like it's always, let me get some other highlighters here. yellow. It's always yellow highlight versus, or minus baby blue highlight. Do you see that? That's the length of that orange line. So this expression would be, well, what is the yellow? Well, the blue is that guy, and the yellow is that guy. Oops. I said yellow is that guy. So all we have to do is subtract the blue from the yellow. Piece of cake. That would be 5 minus x squared minus x squared. And we're squaring it. Why are we squaring it? Because this is squared. Because this is 5 minus x squared minus x squared. And this is also 5 minus x squared minus x squared. Because our cross-sectional area was a square, which means the lengths are the same side. The lengths of each side are the same. Okay, now we just got to find the limits of integration. Well, remember, that's why we set those two equal at the beginning, because since this is in terms of x, we need to know where our first x that we start with and where our last x that we finish with. So we're going to integrate from left to right, of course, and so the first x is negative times negative square root of 2.5, and the last x is the positive square root of 2.5. And if we integrate that, we will find the volume of this 3D shape that's made by drawing squares out of the surface. Okay? Here's another cross-sectional area. Find the volume of the solid whose base is a region in the xy plane bound by the first arc of the y equals sine and y equals negative sine. Oh, that's interesting. So y equals sine would look like this. That's the first arc. Of course, it would keep going, right? And y equals negative sine. Grab a different color. Negative sine, remember, comes like this. Right? So there's our shape. The blue and green are the two boundaries. And whose cross-sectional perpendicular to x equals, or perpendicular to the x-axis. So we're going perpendicular here, not parallel to the x-axis. So I'll draw a couple of shapes here, a couple of lines that give me that idea where those cross sections are. They're perpendicular to the x-axis. And the thing we're pulling out are squares again, with one side and xy plane. Yeah, so these are squares, and you could possibly picture that. If I go over here to the side and draw my square, know that this line here is coming from those guys, right? Because we're taking a square and basically sticking on this. And of course, as this line gets shorter, the square gets smaller. So all we need to do is come up with a formula for that square. Now we know, once again, since it's running perpendicular to the x-axis, that means that the little bit of thickness is going to be in the x direction, so it's going to be dx. So my integral is going to go something squared dx. Why is it something squared? Because that's the formula for the area of the square. We just got to find the length of that yellow expression. So once again, the length of the yellow expression is the blue minus the green. And I think I used different colors last time, but it's the blue line minus the green line. The blue line is sine x, and the yellow line, or the green line, is negative sine x. So we're going to do sine x minus negative sine x. So that would just be sine x plus sine x. So what we're going to put in here is 2 sine x. Isn't that fun? And again, it's squared because this is also 2 sine x, because this is squared. Then we just got to find the limits of integration. Well, the limits of integration is where these two guys intersect, and we know that because we know our trigonometry, that the first time they intersect is at 0, and that second time they intersect is at pi. So we can evaluate that integral, and it'll give us the volume of the shape that's formed by taking this region and pulling squares out of it. Okay. Number 4, find the exact volume of the solid obtained by revolving the region between the graph of, so let's draw a picture real quick. So there's 1 minus x squared and the x-axis. Okay, so let's erase this extra stuff. So there's 1 minus x squared and the x-axis. So that's the region. And about the line y equals 5. So that's going to be, this is 1 right here. So we're going to be way up here at 5. There'll be a line of rotation here. So now we're rotating again. So we're not using the cross-section method anymore. We've got to use either the disk method or the disk washer method or the shell method. Give the sketch of the region. Okay, so if we were to do, well, first of all, we notice there's a hole, right? Because the region is not touching this fix. It's not even close to the line of rotation, so there's got to be a hole in the middle. This doesn't look like a bad washer, so I think I'm going to go with washer. And now, if the line of rotation is horizontal, that means that we're going to be stacking our washers this way, which means the small little height of each washer is a dx, because there's a little change in x. So that's good. We already know this in terms of x, so I'm going to put a pi out here. I'm going to put big R squared minus little r squared, and put a dx here. Okay? So now we just got to find our big R and our little r. Now, the first thing I notice, which makes me smile, is that the big R is the same no matter where I draw it. Whoops. Why does it keep doing that? I want red. Just go to the top of it. There. There's one big R, there's one big R. And you can see that the big R is always the same. It's from the x-axis to the line of rotation, which is y equals 5. So the big R is just going to be 5 all the time. So I put a 5 on there. Little r is different. Little r, grab a different color here, green. I think that's what we usually use. So little r changes depending on where I'm at, doesn't it? It grows pretty long on the outside edge here, and it's shorter in the middle there. But notice it's always between the line of rotation and that line. So that means it's going to be between y equals 5 and y equals 1 minus x to the, or x squared, right? We're doing it in terms of, I'm not erasing. Okay, we'll come back to that. So again, that blue line is y equals x squared. If we randomly pick a point, remember that point is x comma 1 minus x squared, right? And that 1 minus x squared represents the distance right there, or right there, or right there. Those are all the 1 minus x squared examples for each point. So you can see that those green lines are just 5 minus 1 minus x squared. So we'll write that in here. 5 minus, and then we put in parentheses, 1 minus x squared. Just so I don't mess up the negatives. Because you got a lot of negatives in there. Okay? And now I just got to get the limits of integration. Well, the limits of integration are the x values that basically surround or that give you the region, and this is going from that point right there to that point right there. So we just got to find out when 1 minus x squared equals 0. So 1 minus x squared is equal to 0. When? Well, that would be x squared is equal to 1. So that means x is equal to 1 or negative 1. So I'm going to integrate from negative 1 to 1. Okay. This video is getting kind of long, but I think it's worthwhile. Yeah, I don't know if I'm going to do all of these for sure. I'll do one more here. So the region bounded by y equals x cubed, x equals 2. So y equals x cubed looks something like that. X equals 2 would be right there. And y equals negative 1 would be right here. And is revolved about the line y equals negative 8. Ooh. So just come down here. Okay. Sketch the picture of the region and the solid. Find the volume. I'm not going to try to sketch the solid, but so this is going to touch up here somewhere. So that's an interesting shape, isn't it? So you can see that thing is going to, if we revolve it around the line y equals negative 8, there's going to be a big, huge gaping hole in the middle, and it's going to kind of taper out and go down like that. It'll look like maybe like a gopher hole or something, or a prairie dog hole, where they usually kind of build up their dirt around it, and then there's a hole in there, but it's a really big hole, so it must be a giant prairie dog. So this is going to be either washer or shell, and again, we're doing around a horizontal line, so that's if we do the washer, it'll be terms of x, so that's a good reason to maybe try the washer. So if we're doing washer, we do pi times big R squared minus little r squared dx. So then, let's see, dx, yeah, okay. So the big R, well, first of all, the little r I think is easier because you can see that this edge here is the same. I mean, it's parallel to the line of rotation, so the big R is going to be the same no matter where I draw it. I mean, I'm sorry, the little r is going to be the same no matter where I draw it. So, and it's going from negative 8 up to negative 1, so that would be 7. So little r is 7. This is going from y equals negative 1 to y equals 8. That's my little r. Okay, so that's a distance of 7. The big R, we'll draw a couple in here. Oops. Oh, I'm supposed to use red for big R, I think is what I've been doing. Not that it really matters, but. So big R, here's an example of a big R. There's an example of a big R. There's an example of a big R. Now it's different every time, but it's determined by the same two lines. It's determined by that line y equals x cubed and the line y equals negative 8. So we're looking at the distance from y equals x cubed to y equals negative 8. Yeah? Does that make sense? So we don't really have to worry about this part here because, again, we just want to know how long this line is. And that red line is always x cubed minus a negative 8. Right? Now, so that would be x cubed plus 8. Now that you might balk at this a little bit because here x cubed goes down below the x-axis, and so you think, wait a minute, how's that going to work? Well, notice that it should be shorter down here, right? And notice that once the function drops below the x-axis, this term here is going to become negative, so it will be shorter than 8. You know, if we're to the right of x equals 0, the red line is going to be bigger than 8. If we're to the left, it's going to be smaller than 8, and that's exactly what this will produce. Okay, so I'm going to put in here x cubed plus 8 as a big R. Okay? And now we just need limits of integration, and of course this is in terms of x, so we want to go from now. When y equals negative 1, that means we would plug, what would we plug into this function to get y equals negative 1? And now, of course, it would be x equals negative 1. So we're going to go from negative 1, and this one here is x equals 2. We already know that. So that would be 2. Okay? So that, again, if we integrate that, we will find the volume of this kind of prairie dog mound thing around the hole. Maybe I'll do one more because this is about the y-axis. So let me grab blue again. This video is getting really long, but there's a lot of good stuff in it. Okay, so we got the curve y equals x to the fourth. So that's going to be kind of like a extra flat bottom x squared. And the line y equals x, which looks something like this, about the x-axis. Or sorry, about the y-axis. Also find the volume. Okay, so I'm going to erase that part. So you can see here's the little region here, and we're rotating about the y-axis, which means when I stack these things up, we'll have a bunch of, this would be the washer method if we're doing that, so that you'll have a bunch of little shapes like this going this way, right? And so the height of these washers is a dy. So if we're using the washer method, we would do pi times big R minus little r dy, which means we're going to have to change everything. Of course, that's easy to tell, but that means we need to know that this is also equal to y to the 1/4 power. I mean, that's the same equation, right? So if I'm looking at the coordinates of certain points on these lines, we'd have to know that, okay? So now the next thing I'm going to do is, looks like, other than that, we're okay, because the radius is going to be pretty easy to see that if I'm picking one washer, for example, the outside radius is, where's my red? The big R is always going to be determined by that curved line, right? And the little r is always going to be determined by this. Is always going to be determined by the straight line, right? So that means we're looking at the x-coordinate of those lines. So remember, the x-coordinate, so any line on this, if we do it in terms of x, any point on this line is going to be x comma x, isn't it? Because it says x and y are equal to each other, right? And any point on the outside line is going to be like that guy or that guy or that guy is going to be x comma oh, whoops, we want this in terms of y. Sorry. This would be y to the 1/4 comma y, and go back to the green. Any point on this line, that guy, that guy, that guy, would be y comma y, right? We went in terms of y because it's dy. So then, we just got to pick the right. So for the green line, that's the small r. That's just going to be y. And the red line, that's the big R. That's going to be the x-coordinate of the points on this line, which that would be y to the 1/4. Okay? Then we just need the limits of integration. The limits of integration would be in terms of y. So this point down here, of course, is 0. We'll put 0. What is that point right there? That's the point where y equals y to the 1/4. Yeah? And the only place that happens is at 1 or 0. So there's my 0. The other place is 1. And that would be my limits that would be my integral that would help me find the, I always forgot to put that parenthesis in there. It's important to put that in there because that way dy is attached to both pieces of that. Okay, so that would find the volume of that solid that's found by rotating around the y-axis, this little region here. Okay, I think I'll stop the video now because we're at 40 minutes, but hopefully this is giving you some good examples of finding volume. And this worksheet does have a solutions sheet in the module, so you can see the rest of the solutions to the rest of the problems.